Okay, today we're going to be taking T-notes on waves. A wave is a disturbance or vibration that transports energy from one point to another. One thing to note is that this disturbance transports energy, it does not transport matter. This can be seen below in the example. We have some water here, and there is a little rubber ducky right here, and this line is the contour of the wave, and the wave is being shown to travel at time 1, 2, and 3. So this is over the course of 3 different points in the journey of the wave. The wave is going through the water, and as it does, the rubber duck stays in the same place. The rubber ducky can actually be going up and down with the molecules of the water. However, it does not move along with the wave. There are 2 different kinds of waves. The first one is mechanical waves. This requires a medium through which the energy must travel, such as solid, liquid, or air molecules. An example of mechanical waves, we have sound waves, water waves, seismic waves, which are the disturbances that move through the Earth's layers. The second kind of wave is an electromagnetic wave, and this does not require a medium to transport energy. We are very happy for this because this is the reason why we are able to receive sunlight from our star, the sun. And another example is radio and gamma rays. Let's take a look at the parts of a wave. Here is an example of a simple harmonic motion of a spring with a pen, and the ball right here that is attached to the spring is oscillating up and down. And as the paper is pulled, the shape this motion creates is a sine curve as seen here in the diagram. We have the crest here, which is the highest point of the wave, and the highest point is located here and here. The trough, which is down here, also located here. These are the bottom parts of the wave. The equilibrium point, also known as the fixed point, is located here, where the spring would be at rest. While the object is oscillating, it would oscillate equally above and below this fixed point. The maximum displacement from the fixed point is called the amplitude, and that is also from the equilibrium point down to the trough. So it could be from equilibrium point to trough. It can also be equilibrium point to the crest of the wave. Notice that from crest to crest, at the top of this right here, all the way over here to the top of this wave, this is called a wavelength. It is denoted by lambda. It can go from either crest to crest, it can go from trough to trough, it can pretty much go from any point on one area of a wave to the exact point on that of the next wave. The definition of the amplitude is that it is the maximum value of displacement from its rest position. It is the height of the wave. And remember, that is from the fixed position, the fixed point, also known as the equilibrium point, to the crest or to the trough of the wave. The higher the amplitude, the louder something sounds, the higher the volume something is. If you've ever heard of amps, it is referring to how loud something is. And this is an example of a higher amplitude versus that of a lower amplitude. So here we see that the height, the distance displaced, is lower. So we would actually register this as a lighter sound. So something that is softer versus if it's the higher amplitude right here, we would actually register that as being a louder sound. Wavelength, it is the measure of one complete wave or cycle. It is the length of the wave as measured from crest to crest. And that, remember, is the top of the wave to the top of the wave, or it can be from the trough to trough, or it could be at any point along the wave so long as it is in the same place on the next wave. Here is what we call the node, and it is the space that touches the equilibrium point. We have already learned about period, and we know that a period is the time that it takes for one complete cycle of a back and forth motion. This is denoted as lambda and known as wavelength. To find one wavelength, it is just from crest to crest, or trough to trough, or node to node, or at any point along the wave, and then on its same point on the second wave. Frequency is denoted by the cursive lowercase f. It is how many back and forth motions occur in a certain amount of time. And usually we time it by how many cycles are in 1 second. We measure this frequency in what we call hertz, denoted as Hz. 1 hertz is 1 cycle per second. The higher the frequency, the higher the energy, the higher the pitch. So, for example, here we have a little picture where the wavelength is long. This is going to create a low frequency. You're going to have fewer cycles within the same amount of time than if you look down here, we have more cycles, shorter wavelengths, within the same amount of time, the time being 1 second. We would call this a low frequency wave. We would call this a high frequency wave. Here's an example. If I had 1 cycle in 2 seconds and I want to solve for frequency, frequency is, remember, how many cycles in 1 second. All I would need to do is divide how many cycles by how many seconds, and that would give me per seconds. So when I take 1 cycle divided by 2 seconds, I would get 0.5 hertz, which means that I have half of a cycle, half of a motion of a full wave in each second. Another example is if I had 8 cycles, 8 back and forth motions in 2 seconds. That would give me 4 hertz, which means that I have 4 back and forth motions, 4 full cycles in every second. And we can tell that the higher the number, the higher amount of motion, how many cycles I have per second. So 4 hertz is much higher than half a hertz. If we know the wavelength and frequency of a wave, we can determine how fast the wave is traveling. Here's the equation for wave speed. And the speed of the wave is denoted as c equaling lambda times frequency, lambda being wavelength and frequency being this cursive f. The speed of the wave may differ depending on what kind of medium the wave is traveling through. Here is an example. If a large slinky has a wavelength of 0.95 meters and a frequency of 2.2 hertz, how fast is the slinky traveling? When we plug this into our equation, we just need to know the frequency and the wavelength, and when we plug that in, we get 2.09 meters per second or 2.1 meters per second, taking into account significant figures. One type of wave is called a transverse wave. One thing that we know that is true about all waves is that they transport themselves through what we call a medium. Waves or disturbances travel through a liquid, gas, or solid. And when the medium moves a certain way in comparison to that of the energy transfer or the wave, we call it a different kind of wave. For transverse waves, it's where the medium vibrates perpendicularly to the direction that the wave is traveling. You see this when the medium moves side to side, or it creates an up and down movement. This is true for all string instruments, such as a guitar, a violin, or piano. Every time that you pluck, hit, strum any of these strings, it creates a wave that transports itself in one direction, and it moves the liquid, gas, or solid particles perpendicularly. Radio waves and light waves are also examples of transverse waves. Here's an example of a person who is holding a rope, and the rope is being moved up and down, and the motion of the rope is, for example, the medium. So it's either the way that the air, the liquid, or the solid is moving. and then the energy transfer is actually moving from her hand to the direction to the right. So the direction of the wave or the energy transfer is perpendicular to that of the motion of the particles of the medium. Here is a moving example. So if the wave is traveling in the direction from left to right, you notice that the particles of, example, the water is moving up and down, which is a perpendicular direction to that of the direction of the wave. Longitudinal waves are particles that vibrate parallel to the direction of energy transfer in a back and forth movement. Sound waves are examples of longitudinal waves. If you look down here, we have a wave of sound traveling from left to right. The direction of the energy transfer is going in this direction. We have the movement of air molecules that are moving back and forth when this energy goes through the medium. In this case, if it were air, for example, these would be air molecules. The wavelength goes from areas of compression to compression, or it can also be a wavelength of rarefaction to another rarefaction. Now, rarefaction is just where the molecules are spread out more, and compression is when the molecules are closer together. Here is a moving example of multiple particles that are moving from left to right. What you will notice as it moves, this is again the direction of the wave, the direction of the energy, as well as the direction of the particles. So this is an example of a longitudinal wave. What you'll notice is there are compression spots where the particles kind of bang together and get squished, and then they also do expand and get further apart. As you work your way through over from left to right, it also shows little areas of kind of like a pattern of compression, expansion, compression, expansion. All right, that's the end of our TNOTES. Be ready to apply this in class next, and have a great day.